Okay, hi. So today we're going to be going through a paper from the Cambridge International GCSE syllabus. And yeah, if you don't already know who I am, so I am the Argon tutor, a real-life chemistry teacher. So hopefully I can give you some helpful tips and tricks as we go through today's paper. And if you haven't done so already, you can download this PDF so you can be following along, making your own notes as you go through. As we go and answer these questions. So let's get started with number 1. So here we go, we've got a list of substances shown, very, very nice, look at all of those. Answer the question using anything from this list, and yeah, you can use it once, more than once, or not at all. So, so with these I have already written down the answers and then cover them up just because it's a lot quicker than watching me write everything out all the time. So what do we need for photosynthesis? Well, it is of course carbon dioxide. What is bauxite? So this is what's used for the to get aluminium. So aluminium ore, which is aluminium oxide. 2 products of fermentation. Well, can you believe it? We're going to get some ethanol and some carbon dioxide used as a fuel. Ethanol, gas used to convert iron into steel is oxygen. Some of it's disappeared. A greenhouse gas, carbon dioxide, very popular choice today. This should be nitrogen, making up most of the air. And finally, diamond is a form of carbon. So this one can't be carbon dioxide because that's a molecule. So diamond is a form of just pure carbon. Alright, so what do we have here? We have atoms are made of protons, neutrons and electrons. Atoms of the same element are known as isotopes. Okay, so I can fill this one out nice and quickly. So an electron is -1, a neutron has no charge. But both a neutron and a proton have a mass of 1. So this is all very basic stuff. You should be very happy with filling that out. Okay, so now we've got 2 isotopes of magnesium. Complete the table to show the number of electrons, neutrons and protons in these isotopes. Well, let's start off with the easiest one. So protons, it has to be 12 protons because magnesium is the only element that has 12 protons. And because it is not an ion, it's still an atom, the number of electrons is the same. And then to get number of neutrons, it's just the mass number minus the proton number. So in this case, it's going to be 24 minus 12 is going to be 12. And 25 minus 12 is going to be 13. Right, so magnesium has a charge of +2, and this because it has 2 more protons than electrons, and it has the 2+ charge because it loses those 2 electrons to have a full outer shell. But if we just do a quick calculation, so we'd have 12 positive protons, now has 10 negative electrons, so there we go, that's where that +2 charge is coming from. Okay, magnesium ions have the electronic structure 2,8. Give the formula of the following particles that have the same electronic configuration as the magnesium ion. So lots of things will have the same electronic configuration. So a sodium ion would have the same electronic configuration, and this electronic configuration is the configuration of a noble gas. So this is what atoms are trying to get. So we can have more than one atom or ion which will have the same electronic configuration. So a negative ion would be fluorine. That's one example. And neon is the electronic configuration that both of these atoms are trying to get. Okay, in this question, this question is about sodium and compounds of sodium. So describe bonding in a metallic element such as sodium. You may include a diagram in your answer, so I've got it written out here. So it's to do with the other ions. So we've got a lattice of positive ions with delocalized electrons, and where is the metallic bond coming from? So it's coming from the attraction between the positive ions and the negative electrons. So what would that look like? So our lattice of positive metal ions, so lattice just means regular arrangement. So we've got our regular arrangement of ions. How can we show the ions? We can put some pluses in there. So here are the positive metal ions. Then the electrons are just going to be dots. So we've got our sea of delocalized electrons that are free to move. And yeah, the attraction is between the positive ions and the negative electrons. Okay, how does it conduct electricity? Well, we have something that can carry a charge, and it's the electrons. The electrons are free to move and carry the charge, so that's what we need for electricity. Okay, we've got some properties of sodium chloride. Very nice. Name the type of bond in sodium chloride. Well, it is between two ions, so it's going to be ionic bonding. And then explain why sodium chloride conducts electricity when molten. And this is because when it's molten, the ions are then free to move. So the ions can move, but only when it's molten or dissolved in a liquid. Okay, we now have a student. That student could be you. Has determined the concentration of a solution of dilute sulfuric acid by titration with sodium hydroxide. Okay, and then we've got our method here. So we're putting it in a conical flask. We're using methyl orange as an indicator. Sodium sulfuric acid is going in the burette. Adding it until we're getting a color change. Yeah, that's the titration. And then we're going to repeat it several times until we've got some good results. Okay. So name the piece of equipment that is used to measure exactly 25 centimeters cubed. Well, things that can measure exactly 25 centimeters cubed is our pipette. So pipettes are always used in titration because they're more accurate than a measuring cylinder. Our color change for methyl oranges, of course, it's going from yellow to orange. So orange in the acidic condition. And then state how the student decides that a suitable number of results have been collected. Well, once you start to get a collection of good results, then you can stop. So when you're getting 2 or more results that are within 0.2 centimeters cubed of each other, then you have some good results. Okay, now on to a moles calculation. So what are we calculating? So we've got this much acid is reacting with this much base. We've got our equation. So what is the concentration of I keep saying sodium hydroxide. What is the concentration of sulfuric acid? So first of all, how many moles do we have? So this is how titrations work. So once you know the moles of one thing, you can then figure out the moles of the other thing, and then the concentration. So what do we know? Well, we have the concentration and the volume of sodium hydroxide, so we can calculate the number of moles. Here we go. So this is our equation. Concentration times volume, remembering that volume has to be in decimeters cubed, that's why we are dividing by 1000, and then we are getting our answer over here. Okay, determining the moles. So they have reacted in a 1:2 ratio. So if we have a look at that over here. So there's not a 1 here, 1:2 ratio. So all we need to do is divide by 2 to give us the moles of sulfuric acid, and then calculating the concentration. So the concentration is moles divided by volume. We know what our volume is. We now know the number of moles. Again, we're dividing the volume by 1000, and then we are getting our answer. Nice and easy. Okay, now we have a question about sulfur. So sulfuric acid is made in the contact process, and then here we have the 4 stages of the contact process. Okay, so write a chemical equation for what's going on in step 1. So in step 1 we have sulfur is reacting in air to give us sulfur dioxide. So what element is it reacting in air? So it's reacting with the oxygen to give us our equation here. So sulfur plus oxygen gives us sulfur dioxide. What are the essential conditions? So these are the essential conditions to give us the sulfur trioxide. So we have a temperature of 450 degrees, around 1 to 2 atmospheres, a vanadium 5 catalyst, and that's the formula for it there. And here is our equation. So yeah, so this does come up a reasonable amount, so I would recommend, yeah, everything that we have here. Alright, so write an equation for what's going on in step 3. So here we go. So the sulfur trioxide is dissolved in sulfuric acid to give us, name the substance that reacts in, yeah, so this is giving us the aluminium, and then aluminium is reacting with water to give us more sulfuric acid. Alright, now we have to do a dot cross diagram showing only the outer shell electrons. So let's start with hydrogen. So hydrogen only has one electron, so hydrogen is always sharing its one electron. Sulfur is in group 6, so it needs 2 more electrons. So for however many electrons it needs, that's how many electrons it's going to share. So we'll put 2 over here. We've got a total of 6, so we've got 1, 2, 3, 4, 5, and 6. Okay, there we go, nice and easy. Okay, now the balanced equation. So I have balanced this already, so here we go. So yeah, quite straightforward, I hope. Okay, ethanoic acid, so on to our next question. So we've got ethanoic acid is manufactured by the reaction of methanol with carbon monoxide. Here we go, this is our equilibrium mixture. So state 2 characteristics of equilibria. So our first one is, yeah, the rate of the forward and the reverse reaction are equal. So this and this are happening at exactly the same rate. And our second thing is, yeah, the concentration of the reactants and the products remains constant. So that doesn't mean they're equal, but it means that their concentrations stay the same. So once you've reached equilibria, these two concentrations stay the same, and this concentration stays the same, even though they are constantly changing. Alright, so the purpose of industrial process is, sorry, the purpose of this industrial process is to produce a high yield of ethanoic acid at a high rate of reaction. So we want a high yield and we want it to happen quickly. So it's carried out at 300 degrees. The forward reaction is exothermic. Okay, use this information to state why the manufacture is not carried out at this temperature. So if you carry it out, yeah, if it's too cold, then just the rate of reaction is too slow. So this is always the balancing act, sort of balancing the kinetics at the rate of reaction with the yield. So what is best for the yield is maybe not necessarily best for how quickly things happen. So yeah, so the reaction happens too slow. And if it is too high, if the temperature is too high, then yeah, the yield is too low. So the temperature is always a balancing act between those two things. Okay, so let's complete this table. So we have adding a catalyst, yeah, increases the rate of forward reaction. Decreasing the pressure decreases the rate of the forward reaction. And finally, the effect on equilibria. Decreasing the pressure decreases the amount, or sorry, decreases the yield. So that's just to do with, we look at our equation here. So this is 2 moles, 1 mole. Whenever you change something, equilibria wants to kind of shift that change. So if you increase the number of, increase the pressure, the reaction wants to reduce it. So yeah, it shifts this way. Okay. Suggest which of the following metals is a suitable catalyst for the reaction and give a reason for your answer. So yeah, so this is an unfamiliar reaction. It's not specifically stated in the syllabus compared to like the contact process or the Harvard process where you know those catalysts. So this is more testing about your knowledge of the periodic table. So this is a periodic table question. And we need to be remembering that, yeah, the transition elements, they act as catalysts. And we have only one transition element here, which is cobalt. And yeah, our answer is because it is a transition element. So transition elements always act as catalysts. The other metals do not. Okay, ethanoic acid is a member of a homologous series. Give the generic formula for the carboxylic acids. So there we go. Again, just something to remember. Now, draw a structure of a carboxylic acid containing 3 atoms. Well, here we go. So I've got the carboxylic acid structure, but I haven't drawn the rest of it. So it has 3 atoms, and yeah, with this, so this is why I've left it, is that the carbon, so this carbon is included in the number of carbons. So it's part of the functional group and also part of the carbon chain. So we have 2 more carbons, and then yeah, let's get everything else added, so all the hydrogens. So yeah, so with this, it says show all the bonds, so that's including like this bond here. So a lot of the time, okay, so yeah, so with this, that is including, yeah, this bond here. So when you do more chemistry, you kind of don't show that bond. But anyway, just making sure you do for this, because it has asked for it. All right, so when the carboxylic acid reacts with alcohols, esters are produced. The formula of the ester is this, very good. Name the ester. So with this, before we look at the name, we need to sort of break down what's going on. So all of this is kind of the acid part, coming from the acid. And this is coming from the alcohol, and the alcohol is always what comes first in the name. So let's have a look at the name. So yeah, so we've only got 1 carbon in the alcohol, so that's the methyl part, and then 4 carbons in the acid part, so yeah, butanoate. So yeah, so the name is methyl butanoate, and yeah, butanoic acid is the acid that is giving, yeah, it is this, and yeah, so the, yeah, so methanol and the butanoic acid react together to give you, yeah, this ester here, methyl butanoate. Okay, on to the empirical formula question. So we've got our percentages here. So first step, start a column for each element. Then our next step is, yeah, we're figuring out the moles for each element. So with the percentages, you just assume you have 100 grams. So the percentage equals the same as a gram in this case. And then, yeah, once we've done that, we can see how many moles we have. So this is, yeah, moles, moles, moles. Then you always then divide by the smallest number to give us some whole numbers. And in this example, we have not got a whole number. So whenever you don't have a whole number, this is when you then need to multiply everything by 2, which is what we've got here, multiply by 2, which will then give us 3 whole numbers, and our answer, which is this. Oh, come on, which is this. So C3H6O2. Okay, there we go. All right, now we have the empirical formula. We know the empirical formula. We now have the molecular mass. So what is its molecular formula? So to figure out the molecular formula, you need to see basically how many empirical formulas fit into the molecular formula. So what is the mass of the empirical formula? Well, it's 44. How many times does 44 go into 88? It goes in twice. So we have here 2 lots of the empirical formula. So our molecular formula is, yeah, the empirical formula multiplied by 2. Right. We now have a question about zinc and its compounds. So another extraction question, very popular topic there this year. So zinc is extracted from its ore. We've got our 3 steps. So what is the ore which zinc is extracted from? So yeah, so it's mainly zinc sulfide, ZNS, and it's called a zinc blend. How is it converted in step 1? So it is roasted in air, so heat it up in air, getting zinc oxide. Name the reducing agent in step 2. It is, yeah, carbon, which then reacts with oxygen to give you carbon monoxide, which is a very strong reducing agent. Okay, what's going on in step 2? So the temperature is higher than the boiling point of zinc. So there we go. So this is why it's a gas, because you've gone beyond the boiling point of zinc. And yeah, name the physical change occurring when zinc gas is converted to molten zinc. Well, it is condensation, because it's a gas going to a liquid, so it has to be condensation. All right, we've now got some hydrated zinc sulfate. And the zinc sulfate crystals are made by reacting zinc carbonate with dilute sulfuric acid. And here we go. Here is our equation. And we have our method over here as well. Very good. So let's look at the questions. So in step 1, zinc carbonate is in excess. When no more zinc carbonate dissolves. State one other observation to indicate zinc carbonate is in excess. So let's have a look at our equation. Well, we're getting a gas getting formed, so we're going to see some bubbles, but once the reaction has come to an end, the bubbles are gonna stop being produced, so no more bubbles. Okay, name a different substance other than zinc carbonate that can be added to dilute sulfuric acid to produce zinc sulfate. So zinc. So zinc will react with the acid directly to give you some zinc sulfate. Okay, step 1 is repeated using powdered zinc carbonate instead of large pieces. All other conditions are kept the same. The rate of reaction increases. Give a reason why the rate of reaction increases, and you need to talk about particles. So yeah, we're getting a larger surface area, so powders have the larger surface area. What does that mean in terms of particles? Well, we've got particles are coming into contact more frequently, so yeah, so the collision frequency is increasing. And then yeah, the word frequency has to be used. It's a very popular word when we're talking about rate of reaction. Okay, so state what is observed when the solution is saturated in step 3. So you want to see like crystals forming around the edge of your reaction mixture, or you can do the glass rod test. So if you stick your glass rod into the reaction mixture, take it out, you'll see crystals forming, and that's it because the glass rod is colder than your reaction mixture. Okay, using sulfate hydrated, we've got our formula there. Give the formula of the solid form if the crystals are heated to dryness. Well, we're just going to basically be getting rid of the water, so just be left with the zinc sulfate. And there we go, question done. Okay, periodic table, use to classify elements. Group 1, alkali metals, they react with water. Put them in order in terms of their reactivity, so nice and straightforward. Our most reactive is down at the bottom of the group, and then our least reactive is at the top of the group. Hopefully everybody knows that. Name the alkali solution formed. So all of them form a hydroxide solution. So cesium hydroxide. They have low melting points. Describe one other difference in physical properties the group 1 elements and transition elements have. The group 1 metals are soft. You could also say they've got like lower densities. Hopefully you've seen this experiment in school, and you can see you can cut the group 1 metals quite easily with a knife. But do not try that with the transition elements because you're not going to get anywhere. Okay, onto the halogens. So acetine is below iodine in group 7. Predict the state of acetine. Well, iodine is a solid. As melting and boiling point is increasing going down the group, then acetine has to be a solid as well. Okay, now we are looking at sort of displacement reactions, I guess. So group 7 elements react with aqueous solutions containing halide ions. When aqueous chlorine is added to aqueous potassium bromide, a reaction occurs. The ionic half equation is shown. So here we go, it is a displacement reaction. We're just getting rid of the spectator ions. Describe the color change of the solution. So the original color of the potassium bromide solution. So this is going to be colorless as ionic compounds. Well, not all ionic compounds, but ionic compounds with like group 1 and group 7. So if there's no transition element involved, the ionic compounds are colorless. The solution would be colorless. If it was a solid, it would be a white solid. And the final color of the reaction mixture, well, we are making bromine, and bromine has a color, and that color is orange or brown or yellow. You don't have to put all three, but like an orangey brown is the color of bromine. Okay, identify the species that is oxidized. Well, it is bromine, or not bromine, but it is the bromide ion. And it's being oxidized because it has lost electrons. So you can't put bromine here because bromine is the product, so it is the bromide ion that is oxidized, and yeah, it is oxidized because it is losing electrons. Okay, bromine monochloride is made by the reaction between bromine and chlorine. And here is our equation. Okay, and we've got some bond enthalpies and the data. Okay, so we're probably going to have to do calculations here, so let's have a look at what we've got. So calculate the total amount of energy required to break the bonds in 1 mole of Br and 1 mole of Cl2. Right, so you're just adding these two numbers together. And here we go, we're getting our answer. So it's saying, in 1 mole, and these are our data. All the data is given in here, kilojoules per mole. Okay, calculate the total amount of energy released in the bonds when 2 moles of BrCl are formed. So we are just taking this number and multiplying it by 2 because we have 2 moles. And this is our answer. Then calculate the overall energy change for the reaction. So it is the energy needed to break the bonds minus the energy released from the bonds being formed. It's always in that order. And our answer is -4. So from this we know that it is an exothermic reaction because of this minus. So only slightly exothermic. And with that, that is the end. So thank you for watching, and please do like and subscribe and tell all of your chemistry friends. I hope you found this useful. But if you need any extra help, last little push before your exams, then check out my website. The link is in the description, and then from there you will be able to get in contact with me and we can arrange some one-on-one tutoring. Okay, so catch you in the next one. Ciao.